Okay, let's take a look at this problem. It's a word problem, so let's kind of take it apart. So it says in an RC circuit, so RC just stands for resistor capacitor circuit. Our R value is 7 kiloohms. Our capacitance value is 4.5 microfarads. That's supposed to be micro. The capacitor is fully charged at times equal to 0. How long does it take the capacitor to discharge to 35% of its initial charge? Okay. If VC of 0 is equal to 10 volts, I believe this is supposed to be voltage, but it works just fine. V of C is equal to 10, then what is the voltage at 10 milliseconds? Okay. So a lot of information there, so let's go and write all that down. So R is equal to 7 kiloohms, C is equal to 4.5 microfarads, VC of 0 is equal to 10 volts. And we see the word discharge in there. So discharge, that means that if we let it discharge all the way to infinity, that will equal 0 volts. Our time is equal to 10 milliseconds. That's actually the second part. So there's actually part A and part B to this question. So let's just go ahead and do part A first. So we'll say 35% of initial voltage, and then for part B, T is equal to 10 milliseconds. Okay, so that's our given information. So let's go ahead and write our equation out. So if we write out V is C at time, this is going to be charging and discharging, all right? And a lot of people wonder, how do you know if to use the integral equation versus using the charging discharging? Well, take a look at your time constant. It's dependent on that. Can you find a time constant with the information they gave you? In a lot of the previous problems, we couldn't because they didn't give us a resistance to discharge to. So that's why we're using the charging discharging now, because we now know a resistance. Okay. But if we write that out, it'll be, I'll just write V infinity here, plus V initial minus V infinity, E minus T over tau. All right. And we can find, let's see what we know. So let's go and check this off. So we know V infinity. Okay. We know V initial. Let's find tau real quick. So tau will be equal to RC. So 7 kiloohms times 4.5 microfarads. I'm getting 0.0315. Okay, and that's our time constant. So now we know that. Okay. Now this V of C right here, though, we don't quite know that, but we know that V of C at some time is equal to 35% of V initial, which is just 0.35 VO. So we can sub that in. Take this and sub it in there. So now we know that. And the only thing we need to find is time. So let's do it. So writing all this out, so 0.35 VO is equal to 0 plus 10 minus 0 e to the minus t over 0.0315. Okay. And we know that VO right here is just going to be 10. All right. So that'll just be that 3.5 right there. So I'll just go ahead and write 3.5. 3.5. Okay. So we'll simplify some of this down. So we'll get 3.5 is equal to 10e to the minus t over 0.0315. Okay. Now we'll just use the log equation to solve for t. So we'll do natural log of 3.5. Let's divide by 10 first, so that way we can have a baseline for it. So 3.5 divided by 10. All right. And then multiplied by negative 0.0315. Okay. And that's just me rearranging there. So it'll be this value. It's just a little bit of algebra, so you can just kind of work that out for yourself. But that will be that will be 0.033 seconds, which is 33 milliseconds for time at 35%. Okay. So pretty straightforward, kind of a problem we see a lot pop up in the SI sessions. Just get you familiarized with it. All right, so that's part A. Let's go look at part B. So now part B wants to know what's the voltage at times 10 milliseconds. So we'll just write our equation back out. So 10 milliseconds. We'll do 0 plus 10 minus 0 e to minus 10 milliseconds divided by 0.0315, and we're going to convert that milliseconds into seconds because our time constant is in seconds. So reality, this should be 10e to the negative 0.01 divided by 0.0315. Okay. Divided by 1. Good. And when we plug those values in, so V of C at 10 milliseconds, I'm getting 7.279 volts. Okay. And that's all it is. So just that one's even easier, just plugging and chugging into that one. All right. Well, I will see you in the next video.